To get the sprite to move and rotate and to fly itself about the screen, we need to understand a little bit of trigonometry. Not a lot. We're also going to just be able to plug and play some formulas when we're all done here. So we just have to be able to work with a few things. But if you understand and think a little bit about the underlying mechanics, and that does involve some trigonometry, it does make it easier when you start putting your code in, so you're not so dependent on just having an algorithm, a formula that you just put in, go, yeah, well, it is what it is. So the key thing is that when we have rotated our object, you notice that it's rotated as if our unicorn is going to slide up this triangle here along the hypotenuse, so it looks something like this. We're able to then calculate the movement as it moves around on screen, because we rotate and change the angle. But all that's really happening as we rotate and then move at an angle is we figure out what is the angle that we've rotated to. So what is that angle? If I look at a triangle here, I can see right now I have an angle of 31.87 degrees. Now, to move from the center of the circle to the red dot on the outer edge of the circle requires me to know how much am I moving horizontally and how much do I need to move vertically. And it's those two components that we're figuring out. And if I look at it, given this angle of 34 degrees, I can see that if I use the trigonometry methods of sine and cosine, I'm able to figure that out because I know the angle that I've rotated to. I know how much I'm going to be allowed to move each frame. That is the hypotenuse of the triangle. So then I'm able to then calculate my movement. And if I look at a couple things there, so that horizontally, I am moving along the bottom edge of the triangle. We call that adjacent. And I need to know that amount plus the hypotenuse. That gives me my movement on the x-axis. So the cosine of whatever angle I'm moving, I already know my hypotenuse, the speed. All I have to do is solve for adjacent. Simple math. And that tells me how much I get to move horizontally. I use the sine of the angle and the hypotenuse to calculate the opposite, or my vertical movement each frame. So when we think about it in this context, it does allow us to realize if we know the hypotenuse, how much I get to move each frame, my speed, I know the angle that I've rotated, then we can calculate how far I'm moving horizontally and how far I'm moving vertically each frame. That's all the trigonometry is doing for us. And we use sine and cosine to do that. So even if you went through math and never understood what sine was or what cosine was, it doesn't really matter. All that matters is we know that if we know our angle and we know the hypotenuse, we can then solve for my horizontal or vertical movement that I need to do each frame. So if I'm at a different angle, say at 11 degrees, I have a larger horizontal and shorter vertical movement. Now if I'm at a negative degree, you can see the same thing where I have a longer horizontal, shorter vertical movement. Now my vertical is going down instead of up in this case. We'll also notice that we're saying 0 is not at the top, like on a clock where we say we start counting 1, 2, 3 as we work our way around. But we set 0 as pointing horizontally to the right. That is where we say that is 0 degrees. And then we can work our degrees up, or we can start working degrees down. So knowing those values, we're able to then calculate movement. because if we start our sprite at a rotation of 0, so it's just pointing to the right, it's going to be having 0 vertical movement and all horizontal movement. Now, dealing with a rotated rectangle, so when we rotate our sprite and then move it around on screen and want to determine is the collision happening, we can do it with an approximation, which is what we're going to do, because otherwise it requires us to not use simple trigonometry, but we have to use complex vector math, because we have to calculate angle vectors for all 4 corners of each rectangle that's been rotated in space, and then do some math operations to find out, have these 2 objects overlapped, because we have to find out, is there any intersection occurring between the 4 sides of the object. So if we want to know a side, we have to know a corner. Then once we know the corners, we have to plug it in. And you can see that the math starts getting really crazy when we start using 8 perpendicular axes and have to use dot product vector math to determine, are these objects indeed overlapping. We're not going to do that. We're instead going to allow slop to factor into what we're doing, and it's going to be considered close enough. If you think of it in terms of gameplay, what it means is, as a player, you would view it as, wow, that was a lucky escape. I thought I was going to hit that object and I didn't. Instead of realizing that, no, it's just a sloppy collision method happening. Because the reality is, if you wanted to do this kind of math, and we can see that it starts to get pretty ugly pretty fast, what we would really have to do is first do a preliminary collision method of using circle-based collision to find out, are the 2 objects within the same circle, if we work out the maximum circle that could comprise a given object, and is it possible that these objects are indeed in the same physical space? And if they are, then we go into this more complex math, because this is more processor intensive than simple circle-based collision, which we already know how to do. So using simple rectangle or simple circle collision is going to be much easier than trying to calculate all of this fun stuff. So we're not going to be doing rotated rectangle collision. Instead, we will keep it a little bit simpler. Going back into the code, we're just going to simply be loading a single graphic. We're not going to be animating the graphic just yet. We'll have the enemy and the sprite on screen. The sprite will update its position. The enemy is just parked there, and then we're doing a simple collision detection using rectangle intersect between the 2 objects. So we can see there are the objects as we're figuring out with their half widths and half heights, are they indeed colliding or not. So that is similar code to what we've used previously. The enemy is a simple rectangle. Again, when building projects, it's a good idea to start out using simple basic forms and then migrate into complex forms or better artwork once you have worked out the code or programming difficulty. Now, as we move into the sprite, we have a few more options that we need to explore here. So as we are working with it, we can see how we have a couple extra values that have been added in this time of rotation, speed, max speed, and friction. Eventually, when we move into a sprite that can be animated, we will start exploring walking. And part of learning how to do this animated part today is also going to help us with part of what we need to do to be able to build in the animated sequence of the sprite that is walking so that we can move both left and right. That was an issue that we had previously. And this will show us one solution. Another solution is we just make additional graphics and we work with that. And sometimes that's a better option if we have more refined artwork. So the first thing that we need to do is to define out these new properties that have been added into the sprite. So rotation is going to start out at 0. Speed is going to start out at 0. Our max speed is going to start out at 10. So what we are going to do is we are going to set it up through a combination of friction and max speed, so that when our sprite is moving, it accelerates up to that maximum speed, and then it will slow down from that maximum speed. It adds in a nice sense of both gameplay as well as visual appeal when we do that. Now, these values of friction and max speed, as we work with those, we change them around until we find something that is appropriate for our given sprite that we are working with. So we're going to want to determine what is the best value as we work with it. And that's something that will take time to figure out. Now the next thing that we can do as we go through this is we want to figure out how to rotate the sprite when we put it on the screen. So if I run this right now, we'll see that our sprite is up in the top left corner. We can see that the other box is down in the center of the screen. So we need to figure out how to reposition that correctly to fit it on screen, and also how to get it to rotate and move. So what we want is, if I press left, but I'm not pressing right, I want it to rotate to the left. And we do that by setting a rotation value. And then we have to apply this rotation to our object, because we could do it directly. We could just rotate the object directly, and we'll see that we get some really weird stuff happening. So if I put in rotate, and I can specify, see, and this is where we can't really, if we rotate it, becomes a fixed amount, and then we have to determine how we want to rotate it. One other thing to know about wrong. There we go. So if we're rotating something, one thing to keep in mind while we're rotating is that it is using as a unit of measure radians. It's not using degrees. So radians are the values that we plug into sine and cosine functions, which is what we'll be using in a little bit. Radians are just simply another way of measuring our way around a circle. So conventionally, we look at a circle as having 360 degrees. A circle has 2 pi radians around that circle as well. So 2 pi is equal to 360 degrees. So pi is the irrational number of 3.14157, on and on and on and on forever. So if we know that we have pi, and we can represent pi, you can see in the code where we can just type in capital Pi, and that gives us pi. So 2 pi is equal to 360 degrees. So we could do the conversion to our amount if we wanted to. So we could convert from degrees to radians and then put that into the formula, or we can just provide a radian value instead of providing a degree value. And that really is the easiest way to go about doing it. So if we're going to rotate something, we're providing a value in radians, not in degrees. So that will be something to keep in mind. So we don't want to say rotate just yet. But if I say rotation, so if I'm going left, I am going to be adding to my, actually, or subtracting from my degree amount. So we can say -1 plus equals -1, but if I press right, we're going to be at plus equals 1. Now we could use minus equals 1 and plus equals 1, but I like to have plus equals on both of these. So that says we're taking rotation and we're adding to it -1 or adding to it 1. So I like to have the value where I have the minus in front of the value right here. I find that's just easier to see versus having them both at 1 and then saying 1 is a minus and 1 is a plus. And that would give me the same result, but I prefer looking at the code so it looks like this. So now, if we run our program again, nothing's going to happen because we're not deploying this value. But we could simply say rotate our rotation value. And this code is actually optimized for something we need later, so I'm putting some values back in that we will take out just to get the unicorn back in the center of the screen. So now if we run it, we can see it's back in the center of the screen. So I added in x and y instead of just having those at 0 or non-values. So with it in the center of the screen, now if I hit my, whoa, left and right, we can, wow, we're getting some really crazy stuff going on here. And it's rotating. But if we pay attention as I hold the arrow key down to see where it's rotating from, we can see it's rotating from the top left corner. So what is happening here is anytime we use a transformation effect, such as rotate, it rotates from what is the current origin point inside our sketch. By default, that current origin point is 0, 0. So what we have to do is we have to move that point to where our sprite is. And this requires us to use something called a matrix. Now, if we look at what matrix allows us to do, when we are working with the matrix, we're able to then translate to a new location. And when I translate to that new location, then that's going to allow me to reset that point. So the location that I want to translate to, if I look at this, is before I rotate, I want to translate to x and y, which are the location of my sprite. Then I want to rotate around that point. And now this is where we need to get rid of the x and y in both the rect and image lines. So I translate to x and y, then I rotate. Now if we run this again, so now the unicorn is rotating. Now he's rotating really, really, really fast. So what we would realize is we probably want to modify that value. We don't want to be rotating at 1 radian. Now, one way to think about, I said rotation value is 1. But there are only 6.28 radians in a circle because a radian is equal to 360 degrees is 2 pi. 2 pi is approximately 6.28. So if I say I'm rotating 1, that means I'm rotating a lot of degrees per frame. But if we reduce it down to, say, 0.1, now we can see it moves at a much better amount. So if we do 1/10 of that. So it's approximately 6 degrees instead of 60 degrees per arrow press. If we notice, I translated x and y, and then the yellow box indicating intersection has moved. and the enemy sprite has moved as well. We can kind of see it right there on the corner of the screen. So what's happening is if I do a translation and a rotation, that's now affecting everything else that happens after it until we start the frame over. I go back and look at what is happening in draw. I update the sprite. I display the sprite. And then to display sprite, that is where I go translate and rotate. And then I display the enemy. Well, turns out that translate and rotate are still in effect. And then I draw this rectangle indicating the intersection. That's still in effect as well. So both of these, the enemy and this intersect overlay, that yellow translucent that shows up on top, are being affected by this translate and rotate. So we don't want that to happen. So we can take care of that by using the command of push matrix. And when I say push matrix, what I say is take the current transformation information that's been applied in my program, store that in memory, hide that away. Then I go ahead and do whatever I want to do with my new stuff. And then I call pop matrix, which then throws away whatever I did and brings me back to my previous state. So I choose push matrix, do my stuff, then pop matrix. So now when I run it, we'll see that it's not affecting the other objects. So push matrix stores the universe before I make my change. Then I make my change, use the change, and then I say, now go throw away that change so that it doesn't affect anything else. Time to make the sprite move across the screen. So to do this, we need to increase the speed on the sprite. Well, just first start out, if I press the up arrow, that will allow it to move forward. And my speed that I'm going to move forward, I will then try a value of, let's start out with we'll just add to the speed here and see how it goes. So if I press the forward key, nothing is happening, because we also are going to need to figure out how to move it forward. One of the things that we want to do is to apply based on rotation and that forward speed. We need to add to it. So we have to add to our x, and then we'll have to add to the y. Now the amount that we're adding to it, we don't want to just add in a specific amount or a random amount. We're not just going to add in speed, because if we did, we'll see, oh, now it's just moving. That's bad. And we try it again, we can rotate, and it's still, oh, and it keeps, and it goes faster the more I press it. So we got some problems here. So we don't just add in our speed. We need to figure out, going back into the trigonometry of using our sine and cosine to move our correct amount horizontally and correct amount vertically. So the x component is going to use cosine, and the y component is going to use sine as part of it. So if we take and go back into our triangle, so in our triangle we will see that we're moving x. We use the cosine of the angle, helps us solve for adjacent, because the cosine of the angle is equal to adjacent divided by hypotenuse. Hypotenuse is our speed, how much we want to move each frame. We know the angle we've rotated. So if we modify what we are doing here so that we're going to pull adjacent over and set it by itself, we'll see that right now adjacent is divided by hypotenuse. So then if we multiply both sides of this equation by hypotenuse, adjacent, the horizontal movement is going to be the cosine of the angle times the hypotenuse, our speed. That will solve for adjacent. Sine is going to give us our vertical component, or opposite. So again, multiply both sides of the equation by hypotenuse, and then opposite is now equal to the sine of the angle multiplied by the hypotenuse. So that is why we use these values. X plus equals cosine of the rotation value times speed, which is our hypotenuse. Now if we run it again, we'll see we can move. Unfortunately, because our speed is always ever growing, we're going to get going faster and faster and faster and faster, and yeah, that's bad. So we need to put a speed limit on. I mean, we could set this instead of plus equals. It could just be a fixed amount. So we could say it's just equal to 10. Now if I run this, I'll see I press, and it just automatically went to full speed, and there's no way to slow it down or stop it right now. So two things that we can think about doing here. One is that we can slowly speed up, and the other is that we can slowly speed down. And we can speed up to a maximum amount, that max speed we made. We can slow down based on friction. Those are both great ways of working through it. If we wanted to set it up that we have to use the down arrow to, in essence, give ourselves a negative speed so it goes in reverse, we could do that as well. And that would allow us to start playing or moving our sprite similar to, say, the game of Asteroids. The first thing I want to do is to start slowing it down. And to do that, I'm going to do it, if I'm not pressing up or down, I'm going to introduce friction. So what I can say is if speed is greater than 0, then what I want to do is take my speed and multiply it by friction. But if my speed is not greater than 0, else I will set my speed equal to 0. So what I don't want is I don't want to fall into where I start getting a negative speed value where I start sliding backwards. Because if we don't do this where we hard code it into 0, then we will end up where things are slowing down, and then you'll see that they start just kind of twitching on screen. Every so often they keep like twitching a little bit more as they're trying to slow down. So it's better to actually, when it gets close enough to it, that you let the computer round it down and actually kill it to 0. And sometimes you'll want to, instead of having it greater than 0, you might even end up with a small number that you use. And once it gets to within that threshold, then you just kill the speed. Otherwise, you can get some weird physics things happening where it starts doing all kinds of just crazy stuff. So now I can see how it slows down. And right now that's with friction at 0.9. But with that I could go, say, 9.5. And now you can see how it has a more slippery appearance. But now if I were to choose a different number, like say 7, and when I run it, we can see that everything is much sharper and less slippery as it moves. So this friction value is something that you play with to determine the amount that gives you the result that you want in your project. If I were to set it up and say speed plus equals -1 and up is plus speed is +1, and I got rid of the friction part because now we're in space like asteroids. So we can it's just like playing the game of asteroids where we can try and slow it down, except we don't have any screen wrapping going on here, so it's really easy to lose the sprite if it goes off screen. So that doesn't work really well, but it shows that that would be a way to do it. So you could have a negative speed, or you can use friction as part of what you are doing. Oh, I lost it. I went too fast. Let's go. Okay, I lost it again. All right. So a problem I'm running into is if I press and hold the key down, it's checking this 60 times a second. That means by the end of 1 second, my speed was 60, which is really too fast. This is where having that max speed value is going to come into it will come in handy. So what we can do, instead of just setting it so that it goes off at ridiculous speeds, so if my speed is less than my max speed, at that point I want my speed to go up by a small amount. And I'm going to slow it down so it's not quite as ridiculous. So I'll just go up by plus. So plus equals 0.2. Otherwise, I'll set my speed equal to my max speed. So before we just added 1 to the speed indefinitely. Now, as long as my speed is below the speed limit, I'm going to add 0.2 to my speed until I reach that speed limit. But if I'm not pressing the up key any longer, then if I have a positive speed value, speed will be multiplied by friction. Friction is a value less than 1. Because if friction was 1, I would be in space and I would never slow down. Because if I multiply 1 by my speed, I get my speed back. But if let's just say friction was 0.5. If I multiply 0.5 times my speed, that cuts my speed in half. And if I do that every frame very, very quickly, because my speed is 10, after the first frame it's 5, after the next frame it's 2.5, after the next frame it's 1 1/4, then it's going. So you can see how it's going down and down and down. So then it becomes 0.65. So it's going to keep having each time if my friction was 0.5. So within just a very short window of time, I would slam to a stop. If my speed is 0.9, I take whatever the speed value is, 10, and then I get 90% of that. Then 90% of what I get, and I just keep getting 90% of it, so it slows it down a little. So there's a little bit of slipperiness going on. So I go forward, and you can see it slows down. So I get up to max speed, and let go of the arrow, and now we can see how it slows down. So if friction is closer to 1, that means it takes longer to slow down. If friction is less than 0.9, it slows down really fast, knowing that I'm applying this calculation 30 times per second. So again, if friction becomes 0.5, the stop will be almost instantaneous because it only takes a few frames for it to be down to 0. But if it's, say, 0.8, you'll get some slip, but then it stops pretty quick. And if I set friction at 0.98, now we're going to have a very slippery world. So we're sliding because we're almost back in space. It slows down, but not entirely. So 0.9 is a pretty comfortable amount that gives a decent amount of slide, which makes it feel more natural, because if it stops abruptly, it doesn't feel as real when we have smooth movement occurring. The final part is looking at the collision. So we can see the box that corresponds to the unicorn. We can see the box that corresponds to the enemy, the blue box. Now if I move, we can see, okay, well, they're not colliding. That's good. But technically they were colliding there. So if we start trying to find, wow, that was, so we're not touching, yet the algorithm is saying, hey, you just collided. And this is where our method for collision detection is off a little bit. But if I'm moving fast, it seems we don't really notice that slop in the equation. And this is where, if we can make this work in what we're doing, then we call it good. If we need pixel perfect collision detection as part of the project that you build, that requires you to have more complex equations to figure out how to do that. All right, questions? Do we have working code or broken code? Got some broken mo. I'm guessing your code's a little bit behind then too, since you started late on it. All right. All right. So I'm going to point something out here, and then I want you to think a little bit about how you might go about this. To flip the sprite, going back into our animated sprite from previously, if we're not going to build separate artwork that is flipped artwork, which is what we'll be looking at in coming sessions, but if we just want to recycle the same artwork so that we have a lower asset load, which is good in terms of performance. If we have lots of assets we're trying to load, that can cause issues. So the fewer that we bring into the project, the better things are going to be. Well, the first thing I want to declare is that flipped is false, so we're not flipped. So we're starting in the direction that we start in. So we can see that the unicorn is pointing to the right. So it's going to start out and will not be flipped. So what we then need to do is to figure out, so when the gap is bigger on the x-axis, so that we're modifying the x position of the sprite, so we're moving the sprite, then what we want to do is, if the enemy is to the left of the player, so that means that the enemy is pointing to the right, chasing it down based on the current artwork that we have, flipped will be false. But if the enemy is off to the right, which is how we saw it start, and it needs to then flip over so it can chase an enemy that is over to the left, we need to flip it, so we'll say flipped is true. So this is where we toggle that switch, which is going to set it up so that that unicorn will flip. Then what we need to do is figure out how to draw that on screen. And to do that, let's see, Phil is, that can stay. We'll work with that in just a moment. But what we're going to need to do is push the current matrix And I'm going to put in the pop matrix so I remember that. And I'll fill some stuff out in between. So a lot of this code is going to move, and we'll be moving that shortly. So after I've pushed the matrix, every time we push the matrix and want to do a transformation, what we need to do is translate to the point where we want to do that from. So we'll translate to x and y, the same as what we did before. And then we will say if flipped is true, curly brace, close curly brace. So either flipped is going to be true or flipped is not true. So one of those things is going to be the case. So if flipped is true, at that point we now want to, so if flipped is true, this is where we will do scale of -1, comma 1. But if flipped is not true, we'll just set the scale as 1, comma 1, meaning don't do anything. So that's not necessary, but what it does allow us to do is it's going to, the 1, 1 isn't necessary, but it helps us to just keep straight of what is happening within what we are doing here. Now what I want to do if I have flipped it is I need to draw my artwork, so I'm going to take that out of there, and we can put that here and here. But when we draw it, when we translate to that point, we're just going to start out, and I'll put these both at 0. Remembering that eventually we worked our way over to negative half width and negative half height. We'll be probably having to do some changes with that as well. Now, if I do nothing else here, and we run this, we'll see that it works pretty good when I'm over here. Hey, look, you know, he's flipping, except that we can see that the point at which he's flipping on is essentially the tail, so that's where we need to do some modifications to that x value. So much like what we did previously, we can see that so it's close, but what needs to happen is we need to do some further refinements to adjust our positioning. So it's just going to be a matter of fine-tuning what is happening with it, because I can see as it's moving, it's not lining up quite right.